Scoping a project and determining if the project is going to bring significant amount of profit to an establishment is a very huge task, especially when it comes to drilling operations. Um, this is because drilling operations is usually very unpredictable, even with the significant amount of planning that we put in, trying to ensure that the right well is scoped, the right well is designed before we go ahead into execution. Still, there are a lot of risks that could be identified, and we try as much as possible to curb them. Some of these risks we don't even see, and somewhere in the middle of the operation, it occurs, which throws the operations a very big blow and impedes the operations. And in fact, sometimes one goes ahead to overspend, and it makes the investors very unhappy, because at the end of the day, when you overblow your capex or the money invested in the project, it significantly or sometimes it reduces your bottom line, and sometimes even takes you to the negative, which is why it's very important that we have very efficient methods of being able to scope a particular well, do a lot of analysis that will go ahead to advise us if it is required to go ahead with this project or not. Now, sometimes it could be positive or negative, because you might one might go ahead to over place a lot of risk on that project, and at the end of the day, when we over mitigate, it makes the capex go up and scares away the investors. So in this topic, I will be using a case study where we used probabilistic methods. We put in a lot of risk analysis to first of all first of all, select between two options of doing subsea intervention, and most especially, we went ahead to use a decent probabilistic method to choose um, choose between these two methods, and we went ahead to advise the management. Uh, to cut the long story short, we went ahead to execute operations. I'll be running through this project. I'll be running through this topic, and we'll see all the details of what we did, and at the end of the day, see the result of the selection that we made. Good day, everybody. My name is Ugo Koli. I'll be talking to you today on utilizing risk analysis and probabilistic methodologies for subsea intervention operations. So, moving right into the topic, just to let you know, the SPE paper has been written. It's 184261, and the real title of that the topic is actually the use of risk analysis and probabilistic methods for accurate time and cost estimates in subsea well intervention operations. I wrote this paper at the time I worked for Adax Petroleum, and this was actually a well that we what we did was we wanted to see if we could drill through trees, and even though the tree was not drilled through tree, we kind of used them probabilistic methods to kind of to determine if it was worth the risk, and we'll see all that moving ahead. Let me not just go ahead. So the outline of the presentation is, we'll be introducing the topic, which I've already spoken about most of it. I'll talk about the research objective. I'll speak about the background theory, and we'll be talking about the stochastic. We'll be talking about the stochastic and deterministic methods of um, probability. I'll be speaking about the method which we use to quantify the project. Then I'll talk about the results. I'll go ahead to conclude and make recommendations. So moving straight into the topic, what's the objective? We wanted to identify opportunities for subsea well intervention. Then we really wanted to increase our production at the time, but do it in a cost-effective manner. So part of the methods we looked at was, instead of drilling new wells, let's look at wells where the different zones, we had issues with maybe water production, and we really wanted to shut off these areas, or perhaps plug back and do a sidetrack. And instead of going ahead to drill new wells from top to bottom. Now, how was that going to save us cost? We're going to be able to penetrate new reservoirs, or reservoirs that we needed to produce, without having buying all the associated long lead items like the tubulars, the Christmas trees, the completion equipment. So what we just did was get into these wells, shut off these areas. I mean, get into these wells, recover the completions, shut off these areas, do a sidetrack or plug back the area or do a water shut off and go ahead to produce fresh areas. For this well, the plan was to go into this well, kill the well, pull out the completions, and attempt to see if we could do a sidetrack using the Christmas tree, drill the sidetrack, then run lower completions, run upper completions, and go ahead to see if we could increase production. But in between, there are a couple of issues that came up. Would it be possible to drill through this tree? Looking at the significant amount of measured depth we were to drill. Now, this had been done in the past, but the well that was drilled was just about 300-400 feet. So we had to do this risk analysis and see if it was possible to drill through this delicate piece of equipment we see here, which is the Christmas tree. Now, this is what the horizontal Christmas tree looks like. A very expensive equipment at that time was about $7 million, and we wanted to see if we could drill through this tree without having to recover it to surface. So using the probabilistic methods like you see here, risk analysis and probabilistic methods, we use to assess and see was it smart to do through this tree or looking at the risk, because there is risk actually to everything we do, but being able to quantify it, mitigate it, and going ahead to take the right decision on how to address that risk is a very very important skill every engineer must have. So as we move ahead, we'll see kind of what we did to get past this. So for the research objective, just reading out the information we have here. So to describe a method that was used, we used the stochastic method because using the stochastic method kind of throws in a lot. I mean, for both methods, use the Monte Carlo simulations, but for stochastic, you kind of allow it to have a sort of randomness, and it's being able to get into that box of model you have created and pick up a lot of data and use and gives you something that it's possible from the model that you have built, and gives you something from the model that you have built, excuse me. Then one good thing that we should note is I spoke about that in the last slide, that when you underestimate, you could mislead your management. So when you underestimate, you're telling your management it's I mean project is fit for purpose. You can let's go ahead, let's execute. Then in between the project, you see a lot of issues, and while you see a lot of issues, the we now go ahead to overspend and now makes the profit perhaps go to a negative, or the profit realized from the project is not going to be as profitable. Or you can go ahead and throw in all the possible risks, even risks that are not associated to that project, build a huge risk database, and by the time when you do that, you now go ahead to build so much mitigations, and with mitigations, time comes in, cost comes in, perhaps even some equipment that you might not need to try to mitigate those risks. And what happens? It throws your cost up, and by the time you go ahead to present to management, ladies and gentlemen, they run away. So let's get into the discussion. That well was drilled in our college shallow waters about 400 feet. However, it was drilled with a submersible. It was a second generation type. At that time, I think it was a Saipem Skyview 3. It was an anchored rig, and the elevation was about 105 foot. And the well type was a production well. The plan, like I said, was to re-enter the well, recover the completions, drill a sidetrack, and recomplete the well. So this is what the well looked like at the time. And like I said, there were two scenarios. First scenario here to the left, it was to drill the Christmas tree on. So the steps that we're going to run through was recover the debris cap, run the BOP on the Christmas tree, recover into tree cap and the crown plug, which were pretty much the barriers on the tree, kill the well, recover the upper completions, abandon the reservoir, drill a sidetrack with the Christmas tree in place. So you recover everything, all the internals, get in, drill the sidetrack, get out, run your lower completions, run your upper completions, and recover, and then recover the BOP. Now, what do we save? What you save is what you can see highlighted. On scenario two, this is drilling without a Christmas tree. So, what are the steps? You recover the internals, but you will go ahead to pull the before you go ahead to drill, you have to recover the Christmas tree. So that's the extra step. So as you can see here, you will run the BOPs first, recover the internals, abandon the reservoir, you pull the risers and BOP, then recover the Christmas tree, then go back with the riser and BOP, then go ahead to drill. Then after you drill, you now have to suspend the well for a bit, run back and pull the riser and BOP, run the Christmas tree, run the BOP on the Christmas tree, then go ahead to complete. So you see, this is just for this one step, you have these steps if you are looking at both scenarios. Now, what is the advantage of why we're doing what we're doing? Again, looking at this equipment, it's a very delicate piece of equipment. And where we are very, very bothered about is this profile here. Because when you go ahead to recover your internal tree cap and recover the completions, you will have a lot of valves and a profile here that's very delicate. And when you drill with this tree in place, the possibility of having axial and lateral vibrations collide with this very, very delicate part is very possible. And at the end of the day, you might end up damaging this tree. Drilling this well, the sidetrack was about 3 to 4,000 feet. And after post doing the simulations, we saw that this was going to be a possibility. And we had to go ahead to risk assess it. So, looking at the two scenarios, what are the advantages and what are the disadvantages? Because it's kind of going to make us understand why we're looking in that direction. The advantages of drilling with the Christmas tree was going to lower the cost. That is, if everything goes as per plan. However, the disadvantages were we might damage the tree, especially when the Christmas tree is not designed to be a drill through tree. We will have to limit the rotation, that's the RPM. And when you limit the rotation, you will have to slow down your ROP so that you don't have cuttings building. And when you slow down your ROP, that's extra time. And there are shields in this well, especially that this well was, I mean, this was a brownfield. You might have some time shield, some time based, and some shields that will react based on the amount of time they've spent absorbing water, and that can deteriorate, and you go ahead to have stock pipe, perhaps lost BHA, or when you get through it, are you able to drill and pull out of hole? When you go ahead to run your completions, which was an expandable stand screen that was planned, you might not be able to get past this very troublesome zones. But what are the advantages of drilling without the Christmas tree? It's you have more success rate guaranteed, and getting the tree to surface, there will be, I mean, an advantage. There'll be an opportunity to service the tree, and you will not be damaging the tree. You'll be able to spin the pipe as much as you want. You'll be able to clean the hole. Your ROP will be effective, and you'll be able to drill the well as quick as you want to. What is the disadvantage? The disadvantage is cost, because you have to pull the tree to surface. You have to, I mean, all that time running the BOP, pulling the BOP, pulling the Christmas tree, going back with the BOP. So all the timing, and let's not forget, even though this was a second generation rig at the time, the spread rate was about $500,000 a day. So look with the associated timing of pulling out the BOPs, pulling the Christmas tree, that was what we were trying to work out the economics, and but as well with the risk on spotlight. So let's move into probabilistic modeling, which was the tool we used to determine to see if what method, or rather which of the scenarios we're going to be going with. Looking at this next slide, I'm sure you guys are wondering what picture is this. It's a very popular painting by a very, very, very popular artist, and I don't know how many of us will be able to remember who this is. Okay, just to answer the question, that's the Mona Lisa. So to my left, that's what the Mona Lisa should look like. And I kind of associate this to the stochastic method because it gives me the whole everything I need to see: the curves, the color of the hair, what the face should look like, how what the nose should look like, that everything. But if you look to the right, you will see that this is what I kind of want to use to say what the deterministic does. So it gives you something that you would like to see, but it's not going to be as clear cut as it should be. For example, if you look at there's this road behind the Mona Lisa, there's this pathway behind the Mona Lisa. It gets here and it makes it very, very significant. But if you look at the main picture, it's not as it should be. But here it makes it as very, I mean, it makes it very, very like it's an important part of the picture. So that's what um, the deterministic model does for it, because you go ahead to ascribe numbers using offset records, as you just tell it that this is what I want you to use, this is what you should use. But stochastic, you build the model and you let the model take the randomness and build what it should for you, that is going to be close to close to what it should be. So just putting it out, we have the stochastic and deterministic models, defining them and talking about their negatives and positives. For the stochastic, it involves probability and some sort of randomness. Then it provides wide variety of potential outcomes, and it can handle complicated and nonlinear relationships. And the thing about it, the bad side about it, is that a lot of people don't like to use it because it's difficult. I mean, it takes a lot of work to build these models. But for deterministic, your guess is as good as mine. It's a lot easier. I mean, it's done quicker, simple to maintain. You just pick it up and you rock and roll. So, for the deterministic model, what did we do as drill engineers? We took offset records, took the data, put it into the model, which is deterministic, and we use that to build a time curve for the well. But for example, time to pick up pipe, we already know we put that in. Time to So we don't factor in a lot of risk or what could go wrong, the things that so we just go ahead to build all that, and it gives us a time and cost. But for and yeah, sorry, the add-on that we used for for Microsoft Excel there was at risk. But for the stochastic method or model, so we use the same thing: offset records. We use the probabilistic model, and we use that to determine the depth time curve. However, the add-on to it is that we built in the risk, the possibility, things that could go wrong. And when we putting that in, you have to build a lot of other scenarios. And to be able to achieve that, the add-on that we used was the Oracle. And with that, we could do a lot more simulations using the Monte Carlo simulation. So just to throw some clarity on what we did, we were able to build about 15 scenarios. What am I saying? Out of these 15 scenarios, there are a lot of things that could go wrong or that could go right. So say for example, scenario one, are you drilling with the Christmas tree in place? Yes. Did you damage the tree? No. Did you have restrictions while pulling out of hole? No. Do you have restrictions while running the ESS? No. Did you run a dummy assembly just to find out how smooth the wellbore is before you ran the lower completion? No. Did you ever get stuck running the ESS? No. Did you have to abandon and sidetrack? No. Did you recomplete? Yes. Did you have to complete the case to ESS? No. Did you have to suspend the well? No. So scenario one, excellent scenario. You drill with the Christmas tree, you don't have any issues, you run your completions. But let's look at scenario 13. Scenario 13 says you drew the Christmas tree. Yes. Did you damage the tree? Yes. Did you have restrictions pulling out of hole? No. So it deceives you at that time, telling you that your hole is smooth. Did you not have restrictions running into the hole? Yes. Did you run a dummy assembly? Yes. Did you ever get stuck? Yes. So all these have to do with timing. Then did you abandon? Yes. So it's even getting worse. So everything that could go wrong on this scenario went wrong. You damaged the tree, you had sticky formation, you tried the wrong completions, you got stuck, you buried the lower completions, you had to drill a sidetrack. So everything that just could go wrong went wrong on that scenario. So it's telling you that you can get, so this scenario, what we built here was from the best scenario to the worst scenario, and we'll go ahead to see the associated timing and cost on this next slide. So if you look at this in green, that's like our best scenario, and the P10 for that best scenario is the number of days, about 31 days for $32 million, and the worst case scenario is about 60 days for $50 million. However, looking at scenario 13, the P10, that's the best thing that can happen to us, is $55.72 million. Oh, sorry, 55.72 days at 52 billion. And the worst thing that can happen to us is about 87 million dollars for 110 days. So that is a lot of money and a lot of time. So when we now went ahead, so this is further breaking them down. This is just put it in the table so that we can see. In green is our best case, in red our worst case. So when we now ranked them using colors to identify them, with the Christmas tree in place, the best that can happen to us is about 32 days, 32 million, while the worst, 110 days, 88 million. However, without the Christmas tree in place, 34 million. So we can pull the Christmas tree and still achieve it in 34 days, 34 million. Meanwhile, the best thing that can happen to us is 32 days, 32 million. Meanwhile, if it gets very bad, the worst that we can record is 84 days for 66 million. So if you all agree with me, looking at that band, drilling without the tree was the best thing for us to do. So you see how building a very robust model has helped us to identify the best scenario to do this intervention and perform our sidetrack and recomplete this well. So first of all, that was chosen. Then we went ahead to put up an expectation curve. That's pulling all the scenarios and ranking them accordingly. And when we did a probability expectation curve, this was the only place we kind of applied the deterministic mindset. We assumed the P50 and we try to pick the number of days. So the P50 for the number of days is about close to about 56, 58 days thereabout. And for cost, it goes to about the P50. It's about about 48 million dollars thereabout. So when we planned the well using the deterministic method, but however, in house we had to do what we had to do using the deterministic method. But for us to be able to quantify what we're going into, we use the stochastic method to do that effectively. So at the end of the day, this is what the well looked like. We've had a couple of sidetracks, and this was what we did. The last sidetrack, ESS installed, the upper completions installed. The cost for planning was about 41 million, and the duration was for 45 days. Ladies and gentlemen, the actual was about 47 days for 56 million. Now, I'm going to show this table to show to us how efficient doing a stochastic model is, and not just a stochastic model, ensuring that you do a detailed risk analysis and that you factor your risk into your planning before the operations. So the actual 56 days, 47 million. When we used the deterministic method, we predicted 45 days against 56 days. And when we did the costing was 42 million against 47 million. Now, but however, when we use the stochastic model, that's from this, if you can remember clearly, using the expectation curve, yes, this that's about 58 million, and here that's associated cost. When we used the stochastic model, we predicted 58 days. Now compare that to the actual days. That's just 2 days more. And the associated cost, which is about 50 million, compared to the actual, that's about 47 million. So looking at the percentage errors, you can see how efficient the stochastic model can be. So this is 3.5% error, this is 6.38 against the percentage error we have for the deterministic method. So this is just putting out for us to see. I've been taking off the percentage errors for us to see how close to the actual the stochastic model and risk analysis is. So I'm sharing this. Let's have it in mind that this is not just for drilling operations. You can use this method for everything you're trying to go into. Perhaps you're trying to build a house. You are going to factor in what's the cost of materials going up. What's the possibility of of the guys working for you going on strike? What's the possibility of you not getting drilling a decent, I mean, getting the required supplies? What's the possibility of the weather affecting the time at which you're using to build, and a lot of other things. So this is you building a very robust model around that you're going into, and it can be applied to a lot of other things that we want to do. So just putting that out there. So to make our recommendations, it's very important that we apply detailed risk analysis and probabilistic methods to all that we do, and most especially we try and make it stochastic, but because then it becomes very robust. And it's recommended to reference the experience from your offset records, ensure that you build that into the model. You factor in a lot of risk, not just a lot of risk, but risk associated to that event. And so that you don't, at the end of the day, overbuild the model, overcost the model, making your model so, and making your operations and the capex so large that it goes ahead to scare investors. So these are the recommendations that we made. And finally, for future study and technology updates, it is very possible to use regression analysis to create better models, but however, they need to be supervised. But for the unsupervised models, you can actually use k-means clustering, which kind of ensures that you use events very close to the centroid to build your models. And with if you when you do that, it ensures that you don't take unrelated events to that model in doing your costing and doing your risk analysis. So, like I said, the paper you can find out on One Petrol, it's paper 184261, and it's about risk analysis using risk analysis and probabilistic methods. So, this is what our YouTube channel looks like. We have a lot of resources for you to go and reference. We have a lot of shorts for you for, I mean, just in case you don't want to watch the long videos, go ahead to watch our videos, make comments. We want to get your feedback. Do not forget to like, subscribe, and turn on the notification button. That's the link to our channel. And once again, thanks for watching, and see you on the next topic. Bye for now. Okay, good day, everybody. I have a fat girl here who happens to be my daughter, and I have a yes, that's Jaden. Can you say hi to the camera?
Hi. Okay, so this is my dad. He's a YouTuber, like always.
Gabby, do you have anything to say?
What do you say it is? Jaden is 7 and 6.
Okay, everybody, bye for now.
Bye, see you later.